Okay, so for today, I wanted to tell you, about SNT, what we've been working on, latest features, and pretty much an overview of SNT functionality and what can be done in terms of, neuroanatomy in the Fiji ecosystem. Um, uh, but I would like to start first so I was thinking to just give you an overview of what can be done, and then I was hoping that this would be more interactive, and I was hoping that you guys could tell me a little bit of, what are your expectations, what are your needs, and then maybe, I have prepared a couple of exercises for us to do, a couple of, show and tell, a couple of show and tell things that we could do. But it will be important to have your feedback so that you guys could tell me, I'm more interested in this aspect or this, because literally we want to have 2 hours, and otherwise it's not going to be possible to address everything. Does that sound good? Okay, so cool. Okay, so first of all, my name is Tiago. I have been I'm a biologist by training, and I have been working on analysis of neurons for pretty much my academic career. And for that, it started with my PhD studies. I had the need to quantify neurons, and I had very specific needs. And at the time, the software that I had access to was not was not useful. And then and slowly, I started to develop tools for analysis of neurons. And so, so for me and others from the early days, we're talking about almost 10 years ago, I've started implementing our own tools. Those were very scattered across the Fiji ecosystem. There were imagery plugins, some were Fiji plugins, some were macros, some were kludges. And so, and that is pretty much the motivation that then led a couple of years ago to start working on a really more structured, organized, coherent framework where all this functionality could be present. And then once we have that, then we just start building up and having more features. So this work culminated with SNT. I'm showing you here a snapshot from the GitHub page. Just an overview for you who are not familiar with. So SNT is because it's a gigantic library. It's also can be used as a desktop application. So it's a Fiji plugin under Fiji. It can, it has tools for tracing. That's at the core of the retrieval of neuronal reconstructions. It has tools for visualization. It has its own 3D viewer that supports meshes and annotations. A strong focus on single cell morphometry. So this means quantification of neuronal arbors. More recently, has the ability to also make direct comparisons, statistical comparisons between cell groups, which is ultimately what most folks would be interested in, to compare different experimental conditions. And also it has another component that's more related to my recent work here at Janelia, where you can use SNT to integrate to probe circuitry databases, whether it be the fly circuits or in the Drosophila, or in the mouse light, or in the project that I'm running now. And so altogether, the idea is that you now have this mega package that you can use to probe different aspects of neuroanatomical quantifications, but you can use you have the convenience of a single API, and you have the convenience of a single program. There are other things that are more technical, more advanced. We're not going to talk today. So we have also a simulation engine for creating artificial neurons. This is useful for modeling, neurodevelopment, or modeling neuroanatomy. That's we're not going to talk about it today. And then one of the things that has generated quite of excitement, and this is piggyback on the work of pyimagej is that there's been lots of interest in running SNT from Python environments, so we could explore that a little bit today also. So it's the features are gigantic, and so that's why I would like you guys to give me some feedback on exactly what you wanted to address. So the way I was thinking about we could go about this is we could first look at the program as a desktop application. I could show you around a little bit how things work, how they are organized. That will take, we could do that in 10 minutes. And then we have, so a cool thing about SNT is that we have a quite large library of scripting examples, and we use those we use those to document functionality, but also to test function. They're very useful for us to make sure that things are working between releases. And we have quite a lot. We have almost bundled within SNT. We have more than, I think, right now, 80 examples. And on top of it, we have a series of Python notebooks that you can access here from the Python, from the repository. We're going to check that in a little bit. So quite a few of examples. We've made quite a bit effort to have the documentation running, so you can access it on SNT, and you see there's multiple aspects of the program here. You can navigate through this tab here. Have specific details about reconstruction viewer, about a detailed step-by-step manual how to use the program, and also you have quite a bit of some YouTube videos where we try to document little aspects of the program. Okay, so let's just start. So to access SNT, you need to subscribe to the neuroanatomy update site. So you do that through by running the image updater. So update, manage update sites. You scroll down to the letter N, and you find neuroanatomy somewhere, and you have the neuroanatomy plugin here, update site. You have some message that tells you. And when you do that, the program, I'll assume that you're familiar with these mechanisms. So you subscribe, you're going to have a bunch of jars that are going to be installed on your locally on your installation, and then from that you start the program. Once you restart Fiji, you see a button. You should see a button there, SNT. If you don't see it, you can install it by running the neuroanatomy shortcut here. And what that does, that opens this mini dialog, which is the entry point for all the functionality of the GUI. You also find it here on neuroanatomy. It's the same. You have this neuroanatomy shortcut window. And then these other commands that you see here, these are basically maintained here right now for backwards compatibility, so that macros that folks had, macros that existed for these plugins that I mentioned to you that were scattered across different update sites and elsewhere, they can still run. So this is, in our view, this is the this is the most easiest way to access the program, and you can toggle it. You see that it changes colors, kind of a neat thing. It's just a detail, and the idea is that you have SNT, which is the entire program. And when I mean the entire program, means you have the functionality from going to tracing, meaning the segmentation, to the analysis, and then you have things that are more focused on analysis. So if you already trace a neuron, if you already have a reconstruction, then you can use one of those. And I'll show you that in a second. So let's start first with the program. So it asks you what is the image that you're going to segment, that you're going to trace. If you don't have, just say run. And then you can just read everything by default. We can go that. You'll be able to change all that once you start. So that's pretty much the program. It's very discrete. There's nothing. There's not much, sophistication to it, but it is. We try to have it to maintain a good balance between simplicity and functionality. So right now I'm going to start. I'm just going to load the demo dataset from here. I hope you guys can do that on your machines. And so you have a couple of examples here. That's a toy neuron. That's a Drosophila neuron. Let's start with these factor projection neuron Drosophila. It's a 3D image, quite simple, but it's used extensively in several benchmark studies. So, and we use it for to characterize the problem. So that's that's pretty much what you have here. So you can see that it has already been reconstructed the cell. We can hide processes. So here, let's just go for a walkthrough. You have some options for tracing, and now right now I'm showing you functionality for how do you want to display what has been segmented. So you can do, for instance, if in this case I'm selecting only paths that are selected. So because nothing's selected, everything is hidden. And now if I select certain paths here, you only see that one. So that's filter. And there's one thing that is worth mentioning. You see that on the GUI, when you have an highlighted letter, or in this case an integer, that corresponds to the shortcut that you can correspond. So that corresponds to the keyboard shortcut that you can use to trigger that function. So for instance, the shortcut is number 1. So if I just press 1, we don't need any other modifier key. I'm now activated those checkboxes. So 3, 2, 1. If I press L, which is a shortcut for secondary layer, which we're going to talk in a second, I can just press L, and so on. So for snapping the cursor, I can press S, and we find these to be super useful when you want to do expedite tracings. And this is going to be constant throughout the program. Another thing that we find it quite useful, and we had that very positive feedback on this, is that you see these headers that differentiate the different widgets. They are functional URLs, so you can click and you go to the section, the respective section of the manual. And feel free to interrupt me anytime if you if you have any questions. Okay, so this has all been traced, and let's pretend that it has not been traced, and let's try to do a tracing operation here. So just for you to see how it would look like. Okay, so I'm not selecting anything. So the bulk of SNT functionality relies on what is called semi-automated tracing. What this means is that you specify a starting point, in this case, the starting of that accent there. I think you cannot see it very well on my screen. I'm just going to make things bigger. So now I'm in the options tab, and yeah, I'm just making things larger so that you'll see it better. Okay, and I'm going to back. Oh, one detail, you can also toggle these using the scroll wheel. You can also move them around. It's kind of allows you to, so you can put that on the left side. Just gives you some more flexibility, especially if you are on a smaller screen and you want more real estate. Okay, so now the nodes are bigger. Hopefully you can see them. So now I specify a starting point. I'm scrolling along this case the accent, and now I'm going to choose an endpoint, and now the program traces between finds the optimal path between the 2 points. And so a distinctive feature of SNT is that there is this option here in the front that keeps you probing, and it should work as your guide to what is happening on. So in this case, he knows that you trace a segment, so he's asking, do you want to keep that segment? Yes, no. And so if you know, yes, it's highlighted, so I can just press the letter Y, and I can accept it. And then I can press F, and I can press finish. And these are the options. If you find this too annoying, we found that these to be useful for novice, when people start tracing, when they want to know exactly what they have to do, but you can disable all those options here, so you don't need to be bothered by it. Okay, and that's pretty much the procedure. So now your path is there. Now I want to branch points. You can right-click, and you see that there are options here, and then it says fork at nearest node. So let's look for a branch point. Let's say that one there. I'm going to zoom. there, and let's say I want to fork, let's say here. So, you can right click, or that the shortcut now is alt click. It'll tell you, so I can use that. I can use, so I'm holding alt, navigating, so now it tells me that's going to be a fork point. I click there, I end the path there. I'm going to finish. I'm doing this very cursively. And now you see that there is another path that has been created. It was not selected because we have this return option. Otherwise, you would see that. And that's basically the procedure. Okay, so a couple of things that will make things more accurate and more faster. One of them is what we call cursor snapping. And what this means is that you specify a window in 3D, X, Y, and Z. And when you hover over signal, the program is just going to find the brightest pixel at the location. So right now, I'm moving the cursor, and you see that at the bottom, we are navigating in the ZZ plane, and the program is looking for the brightest location in that column in the stack. So we call this signal sniffing. We find it to be very useful. So this ensures that you always are in focus when you are trying to trace a neuron. There are other options, but that's pretty much one of the most common. You can also have shortcuts to click at brightest locations, which you can find here on this menu. And in a nutshell, that's pretty much it. So other things that are important is the algorithm that is used to find the optimal curvature between start and end point. That's Maystar search. We have implemented recently another variant of that. We can discuss it in details. And basically the parameter, I'll explain in a second what that error message was. And then, so there are a couple of things that you can do to optimize that search between the start and end point. You can specify the data structure, and what would mean is that you can either be fast or lightweight. Lightweight in the sense you can use less RAM. So if you have a big image, you probably want to use map, and you can read more about this in the documentation. And then you have different cost functions here, and what these are penalties. These are penalties that will instruct the algorithm to stay on course between the starting point and the end point, very, very briefly. And you have some explanations here. So it tells you, for instance, if your image has a certain property, use histogram, then use this one. If it doesn't have, use this one. If you don't know which one to use, just leave it as default. But there are tweaks here that you can use, and this is actually quite useful because it allows you to trace, in bright field images that typically have more background, and you can ensure that the curvature is going to be more accurate. And then there's other, performance issues. So you can decide. So to do this with the algorithm, when we are performing an A-star search, we need to know, we have to have an idea of the brightness of the signal between the two locations. And so you can have this being computed real time. This means that as the program is, as the algorithm is performing, the search is being retrieved for the neighborhood. But if you have, you can also specify it manually if you have an idea of how your images look like, and there is some guidance on the documentation how to set it up. Okay, so in a nutshell, that's pretty much it. There's one thing that is extremely useful, which we call a secondary layer. So the idea here is that what you are tracing now, you are tracing on an image that, in this case, this image is pretty much, the signal to noise ratio is very high. There's not less background, but not all images are going to be like this. So you can see that this image is pretty much, we can adjust the brightness and contrast, or I can change the lookup table for you to look, but you can see that pretty much there is almost no background. It's, for the most part, is almost, a saturated image. Not all images are going to be like these. And so what is useful is to perform, to compute the curvatures, meaning the tracing operation, the A-star search, on enhanced versions of the image. And so the problem there, so you could imagine you could apply an edge detection filter on this image that would, make the edges more visible. The problem there is that there's going to be always locations, such as, for instance, this gap there, where it gets very dim very fast. So I'm going to disable you know, there are locations in this arbor where no matter which filtering operation you're going to do, you're going to lose some signal. And so then it becomes an issue because you are basically, you know, losing access to the raw data. And so the trade-off that we come here is that we start using here is what we call secondary layer. So basically, what you do is that you compute, you filter your image, you load that into memory, and then you, through a shortcut, in this case the L shortcut, you can toggle between the two. And you are always looking at the raw data, but the curvatures can be computed on the enhanced version of the image, which is much faster. And if you notice that there is some error, you can always revert to the original one. I'm just going to show you how to do this. So basically, you can use our own built-in filters to create the secondary layer, or if you have your own favorite routine, let's say MATLAB or some external software, you can load it here too. So that's agnostic to how the image was created. So in this case, I'm just opening what we call the secondary layer wizard. And so you see that I have lots of operations here. Again, you have to read on the documentation what they are, but these are basically filtering operations that would try to detect tube-like structures on the image, which pretty much all neurites look like, and it will try to enhance those, you know, bring them to the foreground, and basically give a penalty to everything that doesn't look like a tube. And so let's say, for instance, in this case, we can use tubeness filter. In this case, you know, to get the technical, in case you are interested, we are using imagery ops. Some of the filters we have implemented ourselves. And so typically for these filtering operations, you need to know something about the image. You need to know something about the size of the neurons that you are tracing. That can be challenging, so you can just select visually in this case. So he's asking for the size, you say, I don't know. You know, you mouse over, it tells you what he's expecting. So you say, I don't know, and now you say, now click on the representative structure. So I'm going to click here, wait a little bit. Okay, and now you have what we call this prediction palette or preview palette, where basically he gives you different options. He says, I look at the image, I think your neurite is between 0.16 microns or 2.64. And you know, and now you can peruse the stack and figure out how it looks like. So for instance, you know that this parameter here, setting at 2.64, is not going to be very useful because you see there's degradation there. This one also makes the image very dim. You can adjust the palette image. You can change the lookup table to make it, you know, more useful. You can, and by doing these, you can select, you know, the right size for the neuroid. The cool thing here is that you don't need to select. Typically, in an image, you're going to have neuroids that are very large, neuroids that are very small. So you can pick combinations of two. So in this case, I can say, you know what, this one is good. So I'm going to set that as what we call scale number 1. But you know what, this one is also useful. So now you are in a multidimensional space where you can pick as many kernel sizes for your filter as you want. And then we are going to take care of all that internally. Okay, so that pretty much we selected all the sizes. So now I say set. Okay. Oh, I see. And now it's telling you I have repeated my choices. Okay, so I'm just going to remove that. Okay. And now I'm going to commit. Okay, so now it's telling you, okay, so your choices are 0.99, 1.81, 1.48. These numbers are funky because they are scaled by the voxel size. Okay, and now that's pretty much it. And now he's asking you, so do you want to do it for the whole image? And if you have enough memory, you probably want to say that, to say yes. Or do you want to, again, compute locally? And that's basically, that's one strategy is do it once, cache it once in memory, or do you want to compute as you go? Both are, you know, if you have more, depends on your hardware. And then you can specify the precision. If you have a multi-threaded, you know, you can specify how many threads you want to allocate to these. All these options are if you are handling with big images or not. You can also display the image. You can also save the image for later on. And then if you save it, then you could, you know, import it for that menu there. So in this case, I'm just going to say run. I don't know how long it's going to take. I'm probably just using one thread. It's not very smart. I should have selected more. This particular machine, I think I have 32 cores, so this was silly. It's probably going to take a while. But anyway, that's idea. So that's pretty much in terms of tracing. That's pretty much everything in a nutshell. In 5 minutes, that's pretty much what we have. Okay, so I think this is going to, I'll probably have to abort this because we don't have time to wait for this. So I'm just going to kill my and start afresh. Sorry about that. So I'm just going to. Okay, so that that's pretty much it. Do you guys have any questions on this part? Okay. So okay, so back to some example. Okay, so I'm just going to open some example. We could use, well, let's use a time lapse just because it's. Well, by the way, you need internet connection to load these examples. Okay, so here in this is a different case. These are, it's a hippocampal neuron growing across time. But in this case, I just wanted to show you the functionality of what we call the path manager. So the idea is that you have these paths that you typically would want to, review them, edit them, reorganize them, do something with them. And so there's a couple of built-in features for these that make it convenient. So you can tag them, you can say what they are, if it's an axon, a dendrite. You can assign them by channels. You say, this one belongs to channel 1 if you belong to the channel image. Or you can assign colors. In this case, you can say this one is red, and red, could mean, to review. You can type in your own tags, like you can say, problematic segmentation or something. I can say problematic, that idea. But, and the idea is that, you can then use these to access them and do operations on them. Sorry about that. I need to just. And so the cool thing here is that you can, for instance, let's say, tag them by length. So this works as typically the ROI manager works in ImageJ, that if you have one path selected, the command applies to the selection that you have. If you have nothing, then it applies to all of them. So let's say in this case, we want to tag everything with length. Okay, so I have length. He doesn't know the unit because this image doesn't have any special calibration, but now I can do filtering operations. So for instance, I can say, let me select all the branches that have, certain length. So you could say, for instance, give me everything that has between 1 and 6, units. So it's selected one path, and now I can do things with it. I can delete it, I can change color, I can check where it is, I can zoom, and so on. And so this is, so this is extremely useful for creating data and to rearrange things. Okay, so I really need to okay, and so this is something that is extremely useful. You can collapse things, you can reorganize things, you can branch off paths one from another, and so on. So that is, in a nutshell, that's what the path manager does. It's your entry point for all editing capabilities that you need. I'm going back to the same example because there is one thing that is easier to demonstrate on the other cell. Okay, so we have the same neuron here. Okay, so one thing that we do, so far the tracing that we've done is just center lines. It's just center lines tracing. So there are two ways that you can extract diameters from your paths. And those two ways are what we call path fitting and what we call path filling. And these are alternatives. They can yield, both of them can yield results. So you see in this case, this particular construction, you see this line. So those reflect the diameter at that particular node. I can make things bigger for you to see. And so let's work on this one, okay? And so this is going to be a post hoc refinement operation. So what we're going to do here, so now we've traced, we have computed, the location of all the nodes between the start and the end point that we chose. But now what we can do is that for that location now, we can obtain a cross section, try to fit a circle, because again, the assumption here is that these are tubular structures, and so in cross section they will be circular. And then we can, detect the centroid of that circle, and then we can do two things. We can snap the centroid of our curvature to the center of that circle, and we can estimate the diameter of that circle. And so these are going to do two things. You're going to refine the position of the node in case there was some artifact, in case you were clicking too sparsely, or in case you decided to do manual segmentation, which is also an option where you just place nodes without any assistance. And so then what this can bring is bring back the signal to what would be the most accurate, in terms of cross section, what would be the most accurate location of the centroid. And so so we can do this. So I'm going to choose this option. That is like a debug option that's going to explore, and then we see that's what it's doing here. It's very, very small. So I need to zoom that is. So what you're seeing here, I'm just going to, so you see basically that result. So what you're looking now is, you are basically looking at the cross section across all the nodes. So we are navigating through this big accent, the primary accent here. We are navigating through it. I'm going to hide the other ones. And that's basically the result that you get. And so basically in green, you have now the fitted results. In magenta, you have the original ones. And you see that they have some adjustments. And I'm just going to, so you see we are navigating. I just need to reduce this, otherwise you cannot see anything. It's not clear. Okay, so that's that location. We are navigating there. You can look at the manuscript to see which kind of adjustments there are, but that's pretty much the idea. Then you see there is statistical test that is performed. There is a score to know accuracy, and then if you are too far off, you can abort the snapping operation, or you can decide what to do. So that's one option, and that's how you go from center lines to basically a path with thickness. And the other option is using filling, which is I'm going to show you here in this example. Oh, I see. So he's telling me that he doesn't know about the statistics of the image because I have just imported these. I have not traced anything. So I'm just going to trace something so that internally the program can know about how the image looks like. Okay. And so now I'm going to fill it, and I'm going to start the filling. It's going to take a bit of time. Well, you know what? I can actually trace the entire harbor. That's probably more useful. Okay, so you will see, well, it's too fast on this computer actually for you to see anything. You see this green overlay. So basically what happened here is that the program used the seeds of your path, and then it started walking out until the edges of the signal, and then it stopped using the parameters that we specified here, which again you can read in the manual. The default, we're just using the default. And now we're going to store the result. And now we can export it. Let's do as a binary mask, I guess. We can do a binary mask. So now you have a mask of your neuron. So this is a black and white image. It's probably not very, we can do an annotated distance map, which is a projection. So you now see basically those are different diameters. So you can use this for, to mask out, to any sorts of image processing that you need using these masks or using labels. Okay, so that's pretty much it. In this case, it's not very intuitive. If you have to imagine you have a forest of neurons and you have tertiary neuron, you could use these out to mask out all the remaining cells. Okay, so in a nutshell, that's pretty much it in terms of tracing. And now I would like to focus on. Do you guys want to ask any questions about this? Okay, so now we can go to analysis, and you can measure. I guess by now it's obvious what you can do with it, but let's say, for instance, you can look at distributions, certain paths. So in this case, well, you know what? Let's do something. More sophisticated a bit, so we can use. Well, don't need to use. Let's internal distance. That's not particularly useful. Let's use x coordinates, and you can do two measurements. Let's say the next one could be I don't know, number of branch points. It's not going to make much sense, but so you get two histograms. We try to make an effort to make these figures, this publication quality somehow. So they look good from the beginning. You have a dark mode. You can make them dark. You have commands to customize things a bit. So you can put grid lines. You can toggle outlines and so on. You can change the scale. Can make things big and small. And importantly, you can export them as PNG or SVG. You can also export the data as. Okay, so that's one thing. You can measure, of course. You can measure anything that you can measure all sorts of things about these. That's probably just going to select one. Also, in this case, because I've traced one path, so it's telling me I found two cells. I have cell number 2 and cell number 1. Which one do you want to trace? Which one do you want to measure? I can say all of them. And now this is a measurement prompt. So you have all sorts of metrics in here. You can do the total 68. You have to read a bit of documentation of them, but you can search for things here. So for instance, you can look for lengths. Which kind of lengths are supported? You have cable length. You have inner branch length, primary branch length. So you can select the metrics that you want. I say I want to select this one, the complexity index, and then here you can select kind of statistics you want. Do you want the mean, because we are measuring a group of 2 cells in this case. I can select all of them. I want sum. You have commands to select everything. You have some options here. In this case, if you have tagged your paths as axons or dendrites, you'll be able to distinguish them. You can create summaries. In this case, let's just measure. Okay, so that's a table with a gigantic. You have all the metrics here, and then you can create a summary, for instance. Okay, now you have a summary of the measurements that you have for the 2 cells. Okay, so that's all from the GUI. We spent we made a big effort to try to make one of the things that makes SNT special is this idea that it's all about being quantitative, and it's all about being able to quantify neuromorphometry. And so the visualizations are always very, very quantitative. So for instance, you can color code paths. So I'm just going to remove this one here. You can, so for instance, you can, let's say you want to color code paths by their length. So you could go here, let's just color code the cell. So again, let's pick the main cell here, and you want to call them by, yeah, sure, ordinance row number. You can assign a lookup table to it, to the measurements. And in this case, I'm just going to choose the two types of visualizations. You wait a little bit. And so now you have, so in this case, you have a 2D illustration. Again, this is could be useful for publication. You can export this as a PDF. You can Again, there's some customization here. You can move this to dark mode, and then the idea is that now you have a morphometric trait that is being mapped to a lookup table, so it makes it more useful to identify quantitative traits into the image. And this case is the same. This is just using the reconstruction viewer. So it's just now we are in 3D, and we are going to work with the 3D viewer soon. Okay, so that's so the idea is that all the quantifications, again, an effort on being quantitative all the time, quantitative visualizations, ability to select paths and make calculations on them, and then the ability to do some measurements. Okay, so okay, a couple of things that are not well known. I think I'm just going to load another data set. Let's pick sure. Let's pick in this case a multi-channel image. Okay, so I'm going to clear everything. So you have multicolors here. So of course you can trace across channels. So you can specify which channel you're tracing. In this case we are going to, that's channel 2. Let's say we're going to trace channel 2. So I'm going here. I want to say channel 2, confirm. And now I want to trace between these two paths. Say yes, I have one there. Okay, so things that are useful is that you can integrate your regular image processing routines while doing the tracing operations. So for instance, I can pause SNT now, or I can pause tracing, but I can either pause the tracing operation or I can pause the program itself. And from this moment, I just waved the image back to Fiji. So any command now works as usual. So I can obtain, you can do, okay, I'm going to do something silly now. I can, remove some part of the image. I can enhance it. I could apply a filter here. And when I feel that I'm ready, I can go back to the image. And now it detects, it said, oh, while I was paused, I noticed that the pixels change. Do you want to reload the new data? Sure, I reloaded the new data. So this is so that can be very useful. And you can also do things. The idea is that you can integrate these reconstruction procedures with regular, image processing workflows. So for instance, I can convert my path into ROIs. So now I can, I can decide what I want to convert. You want to convert the path segments, the branch points, the tips. These are going to be single points. Do you want to do everything? And where do you want to put them? And I guess one way to put them would be the path manager. So now they're going to appear here in the path manager. So now this is an ROI that you can, if I pause it, it's going to appear as a regular ROI, and you can do things with it. Okay, so that's it. You can also do intensity profiles directly from here. So in this case, so this is kind of neat. So in this case, so we know the center line coordinates, but you can decide a sampling shape around. So you can say, look, I want to do a sphere around each node. I want to take a sphere of 20 pixels, and I want to look at the intensities there. Or you can decide a circle, or you can, depending on the image, scripting, you can find other shapes here. So let's say I want a disk of 20 pixels, and because we are sampling over a large, over a sphere, which metric do you want to use? I want to look at the sum of all the pixels there. I want to look at the median, the variance. Let's say I'll just pick the mean. And now this is just, do you want to do it in pixels or do you want to do it in microns? Let's just do it in pixels. And now you have the intensity profile. So these are the intensities along the path. But the cool thing here is because it automatically, he knows that it's a multi-channel image. So you are now profiling the different channels. So I have channel 1, channel 2, so now we can look at the intensities. And that's kind of cool. Because very easily you can, obtain measurements of your image just, by a simple tracing operation. Okay, so that's it. You have options for time lapse. You have options for skeletonize. You can convert the images into topographic skeletons, in which these are going to be binarized images. That's useful. Has all sorts of utilities. But you can also straighten the path. For instance, that path that we traced, we can pick a neighborhood of, let's say, I don't know, 100 pixels. I guess that would work. And now what you have here is the image. So it's basically the linearized pixels around this path, and this works in 3D, and it also works across the multi-channels, and which can be useful. Okay, so in a nutshell, that's pretty much it. Okay, things that you can do. That okay, so I'm going to load again the same image, just because it's just easier. The starting point. Just going to load. I'm going to load the same projection mirror. Okay. There are things that are more I haven't talked about. I'll let you guys explore. So you can use these side views, and these what they are is that basically it's a synchronous view where you can look at your stack from top side, top bottom or the sides, basically XZ or ZY views, and they can all synchronize. And so what this does, it allows you to, it's a bit anisotropic, the voxel size here, so the scaling is not going to be obvious on your screen. But the ability is that you have all these views that you can rearrange. You have commands here in the view to, organize them. And this basically you have these orthogonal views, and what this does, it allows you can trace an either of them. What this does, it allows you to precise very finely, the nodes, which is an extra level of accuracy. Okay, more sophisticated analysis that you can do. You can compute convex cells. You can do show analysis. That we'll talk about that if you feel there is a need for that. But you can also do things like, you can convert these into a vector graphics illustration. That's what we are doing here. You can export these as PDF, and have some controls. You can rearrange these. You can change the colors. So that's useful to create a figure. You can convert it into a dendrogram. So this is one of the viewers of the program that is not quite accessible. So in this case, you have a dendrogram view. It's quite sophisticated with the things that you can do. You can color code the edges. So right now, we basically are rendering the neuron as a graph. As a tree, you can color code the edges. Again, this idea of quantitative visualizations. You can assign weights to the edge. You can detect weights. You can do, for instance, let's try the color coding, bringing it to in. So you can color code by edge weight. You can just leave it at the regular value. You can set the regular defaults. And you see now it's color coded. There is a legend here that tells you that the weight goes out of lengths between the nodes. And you can do, you can make them thicker, so you can you can say that the maximum is going to be, I'm going to put something exaggerated so that you can see on your screen. Okay, so now they are color coded at and edge, and you can do all sorts of elements, all sorts of visualizations with this. Okay, in a nutshell, that's pretty much okay. In a nutshell, that's the tour. That's fully automated segmentations. You can do it too. So the way this works is through skeletalization. So if you already have a skeleton, so the assumption here is that the signal to noise ratio of your image is really, really good. Your image can be segmented very easily, and you already done that, and you have obtained a skeleton for your topographic skeleton image. We can do that if you want now. So let's load, not the from commands. Let's load data sets. I'm going to open one of the DDC cells. So, okay, so that's one of such images. So you see that this image is a binary one. there's only two values here, foreground and background, 0 to 155. And so these images has already been segmented. And so now the idea is that can I convert these into a reconstruction? And of course, your results will vary depending on the quality of your segmentation. And that's what this is all about here. So it's asking you, what's the source? What's the segmented image? In this case, the data being traced. It could be a secondary image that you had. These options we want to skeletonize, because in this case it's not a skeleton. And then you have options to say, while you are skeletonizing these, what should you do, with branches that are very small? Should you ignore them? Should you consider only branches of a certain size? And also, if two branches are too close to each other, should you merge them? And so, just going to do, I would say that the branch to be real needs to have at least 5 pixels. And I would say that two things need to be connected unless they are, let's say, more than 10 pixels apart. And these, if you have already reconstruction paths, you want to replace them or not. In this case, we don't have, so it doesn't matter. And you can see if you're running there's a debug mode option. If I toggle it on, you would see in the console what it's doing it, what you'll be doing in the background. And so now your reconstructions are here. So because we have a filtering operation, so you have now in magenta. So these are, so I'm just going to change the colors and the sizes so that you can see better. These should have, okay, that's, I think my computer's getting a bit slow because I'm running something in the background. Okay, so now these are things that you can operate on. You can add it. You can, you can delete these one. You can merge them. You can imagine now all sorts of things that you can do. So I'm selecting paths again with a shortcut, as G as a shortcut for grouping paths around cursor. And when I select them, they get highlighted here in the manager. In this case, we have a gigantic collection of paths. So, but they will appear. They are appearing there. So in this case, so this follows the hierarchy of the paths. That's why there's so much. And so you can do. So that could be used in two ways. It could be as a final result, or it could be used now as a starting point for going in and try to correct the result manually. Okay, so that is okay. Any questions? Okay, so let's look at visualization now. So I told you that this reconstruction plotter is the 2D viewer. The reconstruction, we call the reconstruction viewer, is kind of confusing, but it's for 3D images. And this is on its own a standalone application. So you have a canvas that reminiscent of the imagery 3D viewer, and you have some controls here. And hopefully these things are intuitive. So you have controls for the scene. You have the masks here. It should be a tooltip that explains you what they are. You have controls for arbors, for reconstructions. You have controls for meshes. You have controls for reference grains or atlases. You have controls for measuring and settings. And so let's start with loading a data set. So I'm going here to demos, and I'm going, in this case, I'm going to load some of our mouse-like neurons. So those are in the motor cortex, and it loaded 4 cells there. Okay, and it looks a bit funky because they are in the surface of the cortex. You'll see in a second what I mean with it. And I just wanted to give an overview of the capabilities of the viewer. So the mantra is the same. You can toggle shortcuts without modifier keys. And so I can press H for help, and you have a list of the shortcuts that are available. Or if you want that permanently, you can press F1. And you get a dialog that you can keep on your desktop and look at it. Okay, so it's the same idea. So for axis, to look at the axis, I press A. To dark mode, I press D. I can toggle between the dark mode. To reset, I press R. You pretty much see that the latter to log details, I press L. To reload, I press Shift R, and so on. Okay, so these are, in this case, there are 4 cells. By default, each neuron gets labeled uniquely. And this is the same idea of the path manager. You can assign tags by double-clicking on things. So, for instance, I want to say that these, could be my group 1, could be red. You see that it changed the color red. It's kind of neat. You can also, call these, wild type cell. You can call these, mutant or something, and so on. And then you can now, as in the path manager, you have a toolbar now that you can use to operate. Select all the ones that are wild type, all the ones that are red, all the ones that are mutant, and so forth, and you can operate on them. Because the idea is that once you select something, in this case we just have one, then the controls, when you're measuring, they won't, because they are the ones selected, they're only going to operate on them. Drag and drop up should work across the board. So if you have reconstruction files, you can just drag and drop them into the viewer. The same thing for the main canvas. So I'm just going to give you an example. I'm trying to look for some files here on my computer. Something that makes sense, well, or not. So I'm going to delete these neurons. Now you have controls to toggle their visibility. In this case, all. So I can just delete everything. So I'm just going to remove selected because I'm selecting all. I'm going to delete everything, and I can, I can just drag and drop things into here, and they should load. In this case, I'm loading a JSON file from our database. That may not be the right version of the JSON file, actually. Okay, so that was just going to load another neuron. Okay, let's go to drag and drop. Okay, yeah, so in this case, I just drag and drop, and you can draw meshes if you have. So the supported meshes we have are OBJ files. In this case, I just loaded the file. The thing with the JSON is that it's an old format from our database that was never in production, and I shouldn't have dragged and dropped it. Okay, and that's the same idea. So here you can measure things, you can color code. Also branches, you can do the same thing as you did before. So in this case, you can color code this cell, and I can use the same as before. So now you see that your neurons color coded. You can change the thickness of the processes. You can change the orientation. When you control click, you have stereotypic orientations that you can use. So top view, side view, and so on. If you double click, you have an animation. It's quite useful. And you can basically restrain if you just want to move this axis, or if you want to have a free rotation. Okay, so in terms of, so I'm going to delete everything now so that we can start fresh. Okay, I'm going to wipe the scene, wipe everything. Yes, and the bar stay because it's considered an annotation, and those ones persist. Okay, so you can remove all color legends. Okay. So let's load the same. There's an interesting feature here, which is for extra convenience, where you can drag and drop directories, and they will be imported and organized. Each one is going to have their own tags, and then it's going to be immediately you're going to be able to make comparison plots between them. So we could try that also if you are interested on that. So the idea is that you load everything, the groups get segregated, and you're going to have some box plots, some histograms describing the two populations, which could be useful. And there is also an option for some t-tests that are performed by default. Okay, so let's load the same. Let's load Yeah, we could do. Okay, let's load the neuron from fly circuit. So in this case, what we are doing now, so we have built-in support for several databases, and these are databases that host reconstruction data from from connectomics efforts of which will be basically the fly, the adult, the virtual fly brain that also includes larvae, or it could be the zebrafish, not the brain, from the Max Planck, or our mouse flight, or neuromorph, which is like this mega aggregator that hosts reconstructions from published literature. So let's do one from fly circuit. So of course you need to know something about the neuron that you are trying to retrieve. So in this case, we are connecting to their database, and we already know an ID that's populated by default. And you can check if you have access to the database. Just telling you yes, I can connect successfully. So let's just download that neuron. Okay, so that's how the neuron looks like. But then now you will need some context, and so you can go to so you know that this was from the fly circuit. So you can load the reference brain, and I guess that's not. It's outside the volume, so I think that's not the right reference brain. But you get the idea. Yeah. Okay, so I need to figure out why the neurons outside the brain. So that example. Okay, I'll need to look. I'll need to look. So these neurons should have. I guess I'm not using the right reference. I'm not on the right coordinate. That neuron should have been overlaid the reference brain. I think I'm confused about what reference to use. So let's just use the mouse then. That would work. Let's just use the mouse. Okay, so let's just use the mouse. That is what I'm obviously most familiar with. So in this case, we're just going to connect to our database. I'm just going to download one neuron. Sure, I mean, it could be so the same thing. Successfully connect to the database. And in terms of scripting, the API is constant. So these neurons are quite large. So it will take a while. Depends on accessibility. And meanwhile, we can load the reference brain too. So in this case, we want to load the mouse brain. Okay, I think my computer is. Okay, I'm just going to start. I think the graph viewer. Okay, I think that was the problem. You were still connected. Okay, let's start to fresh. I left the pending operation that was falling down my computer. Okay, so I'm going to load the database, house lights, again, one neuron. Okay, so the neuron's loaded. We have the dendrites and the axons. You don't really have a perception of the scale, so let's lose the reference. Okay, and now you have, so that's how the mouse brain looks like, the adult. That's how the neuron looks like. You can browse, and then the cool thing here is that you can load subregions of the brain. So you can look, for instance, you can look for thalamus or the medulla. Let's load the medulla. You are basically now loading, and you can create your own scene. You can see where, for instance, that this neuron does not connect to the medulla. It's kind of obvious. You can load hippocampal information and so on. And because you can also, if you want to find out how to which areas this particular neuron connects to, you can look, for instance, the number of cable length across regions in the brain. And so you can even distinguish ipsilateral. I'm just going to show an example, just going to be easier to understand. And so right now what you are looking at is a graph that has, these are the acronyms for the regions of the brain, and you have the total amount of cable length of that exist in each of the brain areas. So now you can go in and you can load, for instance, the CP, which stands for collocatement. You could load it and see where it is, and you can start doing exploratory analysis. And this would work at the level of single cells and at the level of groups of cells if we had selected them. Another feature that is quite neat is that you can use these for you can do what we call interactive scripting. So each instance of the viewer has a unique identifier that you see there on the top. And so that is going to allow you to script it. So basically you can go here and you can say script this viewer. Okay. I have some funky settings because I just reset my preferences. Okay, so I'm just loading. So you can do, so this case is Groovy. Let's use Python because I guess that's what most people would select. So I'm just going to say script Groovy. Let's change Groovy from Python. Okay. Oh, because I didn't save my preference. That was CD. Okay, just resizing so that you guys can see. And now I'm going to save the preference so that they stay. And basically what you have here is basically what you have here is a boilerplate script, which we have, with all the imports that are required to, and an entry point to the viewer. So you see that the way this works is we are using add parameters. So we have a service that we call SNT service that allows you to access all things SNT. And in this case, we are asking the viewer to ask the SNT service to retrieve the viewer with the ID number 3, which is this one. And now you can do things with it. You could do, what could you do? You could change, you could create an animation, you could hide what we call actors or scenes. You could do all sorts of things, and we are going to give those examples. And this is kind of nice because you could have, you could have an interactive session where you do things by hand, and then you decide, okay, I want to store these, or I want to reproduce these in the future, and then you can create a script. So there is a command for logging in details that presents to the console, which have that minuscule font there. And so I'm just going to paste here. So when I press L, I'm basically logging the scene properties. And then it's telling you that the visible objects are these, and you see that they already know something about the object. So we already set the viewer size of the frame. We already set the bounds. These are the zoomings to the region and so on. So that could be quite useful. And we are just going through some of the examples now with the script. The other thing that I forgot to mention is that there is a sort of command finder on all the SNT. So if you're not sure what a certain command exists, so this button here would list all the commands that are available. So for instance, you want to know how to zoom on an image, it tells you there is that command there, and it tells you where it is. It's in settings, zoom, and then you have to resize this to be able to read that, which is cutting. Yeah, so basically this works exactly as the built-in bar in fiji, or the command bar, or the imagery one, the command finder, which is quite useful. Okay, so let's go. So now we have 45 minutes. I think now it's time to showcase the API and what can be done with it. I guess it makes sense to do it from pyimagej, or do you guys want to do it from the script editor? Okay, so I guess we can do, because we have been operating on, on Fiji's for a while. Let's do it from pyimagej. Okay, so so the instructions. So you see here you have a help menu. You see there's a direct link to the notebooks. I'm just going to resize it. So that's straight from the repository on the, and you have an explanation on how this started and the criteria that you need to have. So I will just, for interest of time, you basically, you need to have Conda running on your system, and you need to have pyimagej installed on your system. And these are you can follow the instructions to have that. So I already set that up here on my computer, and so now I'm going to access. So I've already downloaded these notebooks, and I'm already in that directory. And so now I just need to run this because I'm using Jupyter Lab. I prefer. So I'm just going to run it, and so now I'm accessing the same notebooks that are here on the repository. Okay, and so you have so these are in the tradition of the same thing that you have on pyimagej. You have the sequence of notebooks of tutorials. So it's important that you start first with the most simple one, notebook number 1, notebook number 2, and so on until number 7, which is somewhat more complicated. Not really, but and then before starting, you need to make sure that again these criteria are in place. That you have successfully installed pyimagej, that you have things working, and there are some troubleshooting and some in case you run into problems. But I just went through these instructions this morning, and everything worked smoothly. Okay, so let's go and start from number 1. Okay, so a couple things. In theory, you should be able to start SNT from pyimagej without having to specify a local installation of fiji. However, currently, if you and this is just a temporary issue that is going to be addressed in the future. But currently, if you do that, you do it through an older version of SNT. So if you right now, the most convenient way to access the latest version is if you specify your local fiji installation, and we have a very simple but helpful script to do that, which is this imagery finder. And so it's in the same path as the notebooks. And the only thing you need to do is you have to specify where your fiji application is locally. And again, your fiji application that has been subscribed to the neuroanatomy update site that has so that you can have access to SNT. Okay, so in this case, so that's what we are going to do now. Is basically what this blob of code here is doing is using imagery finder and trying to initialize pyimagej using the local fiji installation. And if it doesn't find it, it's going to prompt you to do so, which is kind of a neat thing, which is what I have here. So in this case, I'm just running. So it says, okay, the default path, I couldn't find it, which was in your home folder. So where do you have it installed? And you see that I have it in a different place. And now you can specify it, and the script now should run. So it's kind of a more extra level of convenience. So it takes a little bit to initialize, get some warnings. Okay, and now it's basically you have now access to SNT. In case you are not familiar with pyimagej, you should definitely check their tutorials. That documentation, the documentation that is amazing, and they have been doing a great work to make everything super intuitive. And so, as you can imagine now, so now we're going to use access Java classes for Python. And so the mechanism to do so is through these site Java. And so that's the declaration that you have to do. And now these are the imports that you would typically do in Java. So scpg.snt is the package where SNT is, and that's the class. So in this case, we want to access the class SNT utils. And so this will allow it to do so. So if you do these, that's the result. So we have successfully used. So which classes do you want to use, you might ask? So you have to read on the API. On scripting, you can click on the API, you get directed, and here you have all the packages that are part of SNT, and you have some a small description of what they do. Here you have core functionality. Here is everything related to analysis. Here is everything related to the graph theory aspect of the analysis, show and so on, and GUI and tracing and so on. So SNT, in this case, SNT utils is just a big, just a convenience class that offers convenience methods to some of the most common or debugging functions of SNT. So in this case, okay, so let's go through the exercise. We want to load the neuron. So in this case, we're going to use just show it a neuron from the mouse-like database. And so for this, we have loader. So you see that it's the package is in the package IO, which you can find it here. Classes for importing reconstructions, and you see that they all share the same pattern. So a loader, if you are loading a file from fly circuit, it will be a fly circuit loader. From insect brain loader. From mouse-like loader, and so on. So in this case, so we import the class. You only need to do this once. Okay, and now you can. So let's do that. Okay, and now you have access to your loader, and then you can go and find out here, and you have all the things that you can do with this loader. And so in this case, we want to initialize a loader for this particular neuron ID. And then if the database is not available, just let us know, like an error. If it exists, then proceed. Okay, so it does exist. So now we have the loader. We're going to extract. So reconstructions in SNT, we refer to them as tree objects. So in this case, the function is called getTree. In this case, when we want just to get the axon, we don't want the dendrite, so we specify the optional argument axon. Okay, so now we have defined an axon, and now you see that there are some Pythonic convenience here where you can, now you have the axon, and you can just simply, if you want to display it, you can just say show 2D, and so what it's going to do in the background is going to create a 2D viewer that's going to have for you to have a look at, and that's how the neuron looks like. Okay, and you of course can zoom out. This is the same. This is the reconstruction plotter in a nutshell. Okay. Okay, so this was in 2D, but the neuron is actually 3D. So I'm just repeating some code. So you can do, you can see already that to do that, you could do axon show 3D. And I'm just going to comment this one out. And the same thing should happen now, but now you have the neuron in a 3D canvas. And if you don't really want to specify, you can also do show, and then it will decide, which viewer, which of the most appropriate viewers is adapted to display the neuron. Okay, here we are specifying a different way. We are actually initializing a viewer. So using its class. So in this case, it's a viewer for 3D reconstruction. So we define it as a viewer 3D, and then you see most of these viewers would have this a Boolean argument that basically defines you want it to be interactive, or do you want it to be, a more headless kind of display where you don't have much access to the controls, but it allows you for more programmatic access of it. So initialize, in this case, we are doing an interactive viewer. It means that we're going to be able to, have a GUI that we can operate on it. And then here are some of the commands. In this case, we are just going to, disable the dark mode. We are going to add the axon. We are going to load a reference brain. We are going to set a view, and then we are going to make it animated by default. You get some warnings, and that's basically pretty much the result. And so you see that in this case we have it. So you are doing this all from the Python notebook, and I have fiji open, but you don't. Fiji is relevant at this point. Okay, so you can do just to show you how it works with image data structures. So again, these are not these are all being rendered from the Python notebook. So in this case, I want to say, look, okay, I want loader, give me the dendrites, and then I'm going to take those dendrites, which remember are a reconstruction, are a tree, and I say, get me the skeletonized image of that and show it, and that's what you get. So that's an image plus object being displayed from here. And then you can do, more sophisticated analysis. So in this case, we want to obtain statistics. So statistics are, because we operate on trees, which are the reconstructions. So the statistical objects are the class that we want to script to access is called tree statistics, for statistics of trees. And so we initialized tree statistics from the axon only in this case, just for simplicity. And now, you can access, you can say, you can ask the class what are the metrics. So I think this is an outdated call. We no longer use the analyzer, which is So you can see, you can see what are the things that you can measure by default. You will have these metrics and you have these other metrics. You can progress. Okay, in this case, so we want to use this particular metric. It's called internal distance, not very interesting by default. And now we can get a summary, a statistical summary of these, and then we can print that summary. So in this case, we are saying that internal distance average is 21 microns, and the standard deviation is 12. Okay, so now that we have, so we can ask the true statistics, we can ask to obtain an histogram of the metric. Now we say get the histogram, and you see the histogram appears here, again with the same commands as before, so it's useful. And now you can do, you can progress and do things. And of course we have, in this case we are using tree statistics because we're just analyzing one tree, but you have group statistics, you have multi-tree statistics, depending on the type of analysis you're doing, group statistics being for groups of reconstructions. And this is akin to what showed before. So in this case, you say, okay, what about the neural peel areas or the areas in the brain where this neuron has presence or which this brain innervates to? And you can also get, from the tree statistics, you can also get a quick summary of the different areas that this brain has. So these are acronyms. They are jargon in the field, but those are basically abbreviations for the different areas. So this would be, the colpotamen, you would see there's a lot of amygdala and so on. Okay, and that's in a nutshell. So that's pretty much SNT running from pyimagej. So you don't need, take home message here is that you now have access to, all the goodies in the Python ecosystem for analysis, and you can do it so independently of having to, running the program from fiji. You can do some more sophisticated analysis. In this case, it's a workbook for convex hulls. So this is a very, in this case, I'll just go through it. So it's the same idea. You initialize as before. Again, we are using ImageJ Finder to obtain the local path of our installed SNT. And then what we are doing here is we want to obtain the convex hull of this termination algorithm. So we want to ignore them in shaft, and we can do so programmatically. So there is a class for convex hulls that allows us to do this. And then, this exercise is a bit more, well, we can run it completely. And then this exercise is going, so I'm going to specify where my fiji installed is. Going to take a while because this particular asset is gigantic. And you'll see that, in this case, we are doing some more sophisticated analysis in terms of the orientation of the convex hull and which are the main axes that they that the hull will have. take a while to run. I think those are it's a neuron with 5,000 nodes. Okay, so that's the first figure, and that's the last favorable one. And you see that in this case it uses PCA to try to look at the orientation of the main axis of the convex hull, which is kind of a neat thing. We have examples here where you can do things using Blender, which is Python based. But I'm just going to show you here an example where you don't need to declare at all where your local fiji installation is. So the way you initialize pyimagej is like this. So you want the package fiji because we are dependent on fiji dependencies. And you specify SNT in a Maven type of way. So that's how we define the coordinates for the SNT package. And in this case, you don't need image finder. You don't need to specify your local. Installation, and you can just run this from an environment, which simplifies things quite a bit. But again, currently, the only limitation is that we need to run an older version of SNT until this is solved. And there is, you can keep an eye on this issue until this is hopefully should be solved soon. Okay, questions. Okay, do you guys want to look at the built-in scripts? I guess we could do that. Okay, so from the script editor itself, so you see in the templates menu, you have neuroanatomy, and then you have a series of scripts that exemplify SNT function. And then you have, they are split by categories, but they also are split by language. So you can look for language, you can look for, all the Python neuroanatomy scripts, or all the bean shell scripts. We try to diversify and we try to have examples for different languages. You see that the majority, however, are Python and Ruby, because that's the languages that on a daily use, we tend to use the most. But I'm just going to show you an example. I guess we could use this example. Okay, alpha filling. I don't know if this. We try to have all the examples to have them self-contained. So if you don't specify an image, you should run on the demo image. But it's not always possible to specify, to have data available all the time, and some scripts may require a proper local image to be available. I was going to mention as we're trying to make work on the API for SNT and try to make it script friendly, we also made some improvements to the script editor. I can just go for them easily. So one of them, which you may have already noticed, is autocompletion. So especially in Python, you can just do, you should be able to autocomplete things as you type. Let's see if I have the options set. Autocompletions. Okay, and you can use see. Okay. Sorry, I just changed this. Let's go to see. Let's do, for instance, so what we have declared here. Well, this would make more sense. Well, okay, let's do like this. Let's start in the script. Okay. Oh, I have a comp. That's funny. My autocompletion is not working, which is strange because Okay, so I have, yeah, that's the problem. I'm using my own version of Fiji to demonstrate this and on this workshop, and for some weird reason, I think I broke it one in the autocompletion, which is a bit silly. It should work. Yeah, it's not working. Okay, anyway, on your installation, it should work. Basically, as you are typing, you should have autocompletion for the imports that are available, and you should have autocompletion for the methods also that you are accessing, which is, and we also had it in a way that you could, you also have types and declarations for JavaScript in case you prefer to use that instead. It's very frustrating. Yeah, there is no. I think I have a shortcut conflict on mine. Anyway, let's just run the demo. So you'll see what this does in a second. Okay, so in this case, we are taking a reconstruction, okay, and we are taking its, we are basically performing a filling operation. And I was just going to project this so that you can see it better. That is fully programmatic. So basically the operation we've done before, so the idea is that we have the center lines, they are 2D, we load the image, we load the reconstruction, perform the filling in the background, and then we obtain a mask, we obtain a labels image. So in this case, each branch is a unique label. As a unique label, we can do set things so that they are more visible. So basically, every single branch of this neuronal is a label. We can use this for image processing, and that's kind of it. And this can be all done programmatically. There are other examples that one could run. Boilerplates are things for you to start with. So, for instance, if you fancy Groovy, you have just a boilerplate that you can start with that has all the imports that are required for most common operations. We can have and run this example. Also, the idea of these examples is that these are going to be used for you as a starting points for your own routines. In this case, it takes a neuron and it tries to find so it's a mouse-like neuron. It loads the area that is associated with the soma and the area they are associated with the terminals, and then it tries to find the shortest path, the longest path within the arbor between the two images. We get asked a lot if SNT supports image macros, and the answer is no, we don't, mainly because we don't use it, and so it has not been a priority. However, there are ways to have a macro-like behavior, and maybe we can talk about those now. And so I think so we can go for the tracing. So for instance, that's through script tracing and interactive tracing. So the idea here is that this script assumes that you have traced something, you have done some, some searches by yourself, but you also have, and you also want to blend that with some automated scripting, so automated tracing. And so let's just go through the anatomy of the script. You have some parameters that define the services that are going to be required, some imports that are important, or so these are the classes that you need to access. Okay, and so the SNT service we define it here as SNT. So basically, what this is doing, and we have the explanation there, is we're querying the SNT service to say, get me the GUI of the program. And if the GUI does not exist, then start one. Okay. And this is just, when you initialize a program, you can specify a path to an image, or you can specify some keywords. In this case, we're saying demo, just start in demo mode, or with the demo image in this case. And these, it's a Boolean flag that tells you should the GUI be displayed or do we want to work Atlas. And the advantage of working Atlas is that you could run it from a cluster or you could run it from something else. Then there are some, because the idea is that this is supposed to be an interactive session. Now there's some, these we are just being careful in case the GUI did exist, and let's make sure that it's ready. If it's not there, it's just pop up a message and say, please stop, doing what you're doing because I want to run, something like that. And so, and then you can access different things of the plugin that is running. In this case, we are doing something that is quite silly, but what I wanted to show you is that it is possible in the API to run commands. So you can, so we can see it here on, so let's go to the API. So we're going, in this case, because we are using the GUI, so we are going to look for the GUI. And you see that there are, different, these correspond to the different dialogues, the different components. But what we want to access in this case is part of the core SNT, which would correspond in a nutshell to these two windows there. And so in this case, we are going to, let's try to run a command from the path manager. So the path manager is path manager UI. You can see it here, implement path manager dialog. Okay, and you see that there are some commands here that we can script, and there is a thing in here that says run command. And so if you read the description, it says the command to run exactly as listed in the path manager menu bar or right-click contextual menu. So what this means is that, now that we have something, something running, we can just, we can, I'm actually going to delete all that and simplify things a bit so that we can, okay, so if the GUI is not present, start one. And now that the GUI is present, we can just run a command. Okay, so now we can just do, and again, with autocompletion, this would have been perfect. It's just unfortunate that it's not working for me, but it should be working for you guys when you try this today or later on. So now you can see it. So, so this particular method is run command, and on the GUI, so we can just say run command. And the key thing here, and is a bit, it's the restriction is that it needs to be typed exactly as it is listed on the menu. So let's see, for instance, okay, so let's, this particular command is called trace channel. So we are just going to see if that works. Trace channel. Okay, we can try to run. Well, because the image. Okay, so I think that didn't work. So we got an exception because it's telling us that that command does not exist. It probably has a space somewhere. Okay, that was probably, you can see the frustration of this. So you basically, this only works, it needs to be typed exactly as it is. So I either missing an uppercase or I'm using a lowercase, or there is some white space either as a prefix or a suffix that is not working. But so this is the current limitation, but this would allow you to have a macro-like access to the program. We haven't worked extensively on this, as you can see, but one option that we could have is that we could have a sort of recorder that every time you click on a menu, you would record the exact string that you could then plug it in. If folks find that useful, please let us know, either in the forum or on GitHub, and that would be something that would be very easy to implement. As a reminder, you have this command finder here, so you can look for things here. If you don't know where they are, if you find it confusing, it tells you where they are. In this case, they are in the path manager, PM, and so if you click there, you have just run the command. In this case, we don't have any paths open, and so it wouldn't work. So we can try to trace a path on this particular neuron. Yeah, okay, continuously. Oh, I see. We have two instances of the same problem. It's probably that didn't help. Oh, I see. I see. We just will. Oh, I see. Mm-hmm. Yeah, I think we. Yeah, okay, so there is still a typo on the. Yeah, there's probably a white space issue, or we need to figure out exactly what. So that's the current limitation. Again, it's not because the reason why it remains fragile is because we don't find the need. We find the scripting API might be more powerful, but if folks think that this is something worth pursuing, could be a future addition that we could implement. So do you guys have any questions, or do you want to test, do you have any data sets that you would like to test, or do you want to showcase anything? Okay, if that no more questions, then thanks a lot, and see you guys in the forum, or see you guys around, and let us know if you what you end up doing with SNT. Okay, take care.